Hello physics students, welcome to video 3 on circular motion, and let's just quickly try and have a look at some applications of what we just learnt. We learnt how to use the equations, so let's just put it in a real world context. Here's a couple of examples of circular motion. The first one would be a washing machine. Some of you probably have front loading washing machines which effectively work on the same principle as a top loading, just on the side. You can't open the top, it doesn't leak. These guys, they all spin at a fast rate when they're in the spin cycle to get rid of the water out of the washing, and so they have a perforated drum and then another drum that collects the water, and that's an example of circular motion, because the spinning, to keep spinning, the water to stay on the clothes has to cling to the clothes with enough force to overcome the centripetal force. And as soon as you can break that surface tension between the water and the clothes, the water gets flung out and ends up going through these holes. And so these guys are programmed to rotate at such a rate, actually the faster they rotate, the more water they get out, because it's only the surface tension of the water clinging to the clothes that keeps things wet. And so that's how these guys work. Classic example. Now you may, if you've been on a boat or a big fishing boat or a cruise boat, been up on the bridge, you would have seen that on the bridges of larger boats that go out into the ocean, they would have had one of these guys probably, and it's a clear view screen. What it is they punch a hole through the screen and they replace it with this disc, and it's a clear plastic disc, and it rotates and it spins basically, and you can have the worst weather outside with waves smashing over the bridge, and your poor old wipers, they give up the ghost if there's too much water. They just can't keep it clear. And so this was invented, it was actually invented in the Second World War for the warships that were going in the North Atlantic, which are notoriously bad seas, particularly in winter, and it allowed, basically any water that goes onto this is flung off straight away, and so you have a constantly clear vision. The water doesn't bead or pull, and therefore you have a nice clear view. And you really only use it during the worst possible weather, but that's probably when you actually want to see what's out in front of you. So that's been around for a while. Now this is an example. These are a little bit more out of left field now, but this is an example of a machine that they're testing in a lab, and the idea is when humans go off into deep space, they're going to spend long periods of time in zero gravity, and that affects our bones, our muscle growth, all sorts of things, and basically astronauts get quite a lot of wastage. And so if you're going off to Mars or somewhere, you don't want all the astronauts to rock up to Mars but not be able to walk around because they've got no muscles and their bones are too weak. And so this is one of the ideas. Here you've got, or you would have, two astronauts. This guy is actually sitting in a chair pedaling, so he's getting a lot of exercise, and this guy is strapped in on this platform that swings around, and this astronaut would be experiencing G-forces, which you wouldn't experience in space. So it's actually a way of getting an artificial G-force sensation in space, in a limited amount of room, which they would have on any spacecraft. So they're still testing all that sort of stuff and working out what works. Generally speaking, people get quite nauseous being spun around like that, but then astronauts are tested to be people that aren't sensitive to that sort of things, because they put them in those big centrifuges that spin them around to test their motion sickness capabilities. So that's an interesting use that's still being developed. And this is an old one where they used to spin people around in a similar idea, and it was supposed to be a cure for madness. And so they put a mad person inside the thing and spin them around, make them super giddy, and then release them. This was a long time ago when medicine was very much an art, a mystic art, and so not necessarily much science, but some people are actually revisiting. This is an article from New Scientist, and they're revisiting the concept because it was noted that some people actually got a degree of improvement from a treatment of having themselves spun. Why? To the scientists, you would go, well, why would there be an improvement? And you'd have to actually have a cause and effect. Whereas in medicine, they often just do things, and if they get a better result, that's it, they keep doing it. They don't necessarily always try and work out why. But there, a human centrifuge. Now, cars go around corners is classically an example of circular motion, and this is a force diagram. It's got a whole lot of forces. We've got the individual forces of friction from the tyres, we've got the weight force here, we've got the normal force from each of the 4 tyres, because the ground is pushing up with an equal but opposite force to the weight force, and then most importantly, all these friction forces add up to provide the centripetal force, which is the force that allows you to go around the corner. And on a flat road, it's pretty straightforward. Here they haven't bothered drawing the individual weight forces and friction forces. They've condensed it down to a normal force, a weight force, and the centripetal force. And so this car would be going around a corner. Now, why do they bank corners? If you're driving down the highway or you watch race cars, you often see that corners are banked, and they're banked because of physics. The physics is that when you bank a corner, you have a component of your weight force. Alright, that's your weight force, that's your normal force perpendicular to the bank. This component here of the weight force, or the normal, is actually in the direction of the centripetal force, and therefore the weight of the car pushing on the bank and the bank pushing back enables you to go around that corner faster, because you need less friction, and that's why they bank corners as they do. The opposite scenario is when you have a bank or a corner that's canted in the opposite direction, in which case you actually have to go super slow, and are very dangerous. And nowadays you don't have, on the highways, you don't have many corners that are canted the opposite way, because they're just accident prone. But it makes life a bit tricky. But in some sports like rallying and stuff, you do have those sorts of situations, and the drivers have to be very careful. Now, clearly, as you increase this angle of banking, this component here would increase more and more, and therefore you would have to use less and less force to actually go round in the circle, because you're using a larger and larger component of your weight force. And that's why in some circuses and entertainment things, and if you go onto YouTube, you could see videos of people riding motorbikes around on a vertical wall, or even a car. They have the dome of death, all these sorts of things, because they're going fast enough that the wall is pushing back and providing the friction force and the centripetal force required. But we wouldn't work in that much extreme, generally speaking. Alright, yeah, and in our OneNote there's probably a couple more videos, remembering that vertical circles are not actually in our course. There's a plane loop one, there's a fifth gear, which is a motoring show, sort of like Top Gear. They decided to do a loop-the-loop in a car, which was got a lot of physics in it, and there's one called loop-the-loop vomit, whatever that would be. And that's in your OneNote. Alright, so have a look at those. Hopefully now you know everything you need to know about circular motion, and you're able to do all the questions. And if you have any questions, remember to ask me. Cheerio.